Okay, semua boleh nampak skrin saya? Boleh dengar?
Boleh, Doktor.
Okay.
Saya nampak.
Okay, last week we have stopped until this slide about isotropic antenna. Okay, so we are now in the second topics of chapter 5 about antenna. Okay, so the purpose of antenna is to radiate the electromagnetic signal to the free space. Okay, and also to receive the signal from the free space so that we can do the process and get the original signals back. Okay, so in antenna, when we learn about antenna, there's a one antenna that we call as a reference antenna. Okay, antenna yang menjadi reference atau perbandingan. Okay, so the reference antenna is a theoretical antenna. So we also call it as an isotropic antenna or isotropic radiator. Okay, juga dipanggil sebagai isotropic radiator. So So this isotropic antenna is also known as the isotropic radiator. Okay, it's a theoretical antenna where it does not exist in the real world. So if you see from this picture, the isotropic antenna is a small dot at the center over here. So this isotropic antenna, among the characteristics is that it will radiate the electromagnetic signal in all directions. Okay, so salah satu sifatnya yang pertama adalah dia akan memancarkan gelombang elektromagnet dalam semua arah. Okay, so we're going to see that the radiation patterns, okay, the radiation patterns shows the patterns of spherical. Okay, bentuk radiationnya adalah bentuk spherical. So be careful, this spherical is not the antenna. Okay, this is the radiation pattern. The antenna is at the center over here. Okay, antenanya ada di tengah-tengah sini. So it will radiate the electromagnetic energy in all directions, and the shape of the radiation patterns looks like a spherical shape. Okay, itu adalah sifat yang pertama. And then the next characteristic is about the gain. The gain. Okay, so here we have two kinds of gain. The first one is a power gain, and the other one is directivity gain. Okay, so power gain GP and directivity gain D, or you can also write as GD. Okay, it doesn't matter. So in isotropic antenna, it has the gains both power gain and directivity gain equal to 1. Kedua-dua jenis gain ini bersamaan dengan 1. Okay, remember in antenna, you will learn later that in antenna we have two kinds of gain. The first one is power gain. The second one is the directivity gain. Okay, so you're going to see the difference later. Okay, I think we already learned about the difference here. Okay, you will see about the difference in terms of gain later. So, okay, no problem. Kita akan lihat gain nanti. Okay. Later we're gonna see the difference between these two kind of gains. Okay, so a true isotropic radiator, however, does not exist. Okay, so dinyatakan di sini it does not exist, but it closely approximated by an omnidirectional antenna. In the real world, we have an omnidirectional antenna. Okay, here we have in the real world we have the omnidirectional antenna, but the characteristic is not like the isotropic antenna. Okay, the gain is not equal to 1 for isotropic for omnidirectional antenna. So this is the real antenna. Closely similar, almost similar with the radiator where it radiates the electromagnetic energy in all directions. But it is not like the isotropic antenna. Dia tidak seperti isotropic antenna. Okay, dia tidak sama. So, the purpose of this isotropic antenna is used as the reference when we design the real antenna. Okay, apabila kita design real antenna, kita menggunakan konsep isotropic antenna sebagai theoretical comparison. Okay, so that we can design, we can build the real antenna. Okay, so this is the references. This is our references when we want to design the real antenna. Okay, and antenna gain. So we have here. Okay, so antenna gain. Uh, First is the directivity gain is equal to P power density divide with the power density of the at some point given antenna given. Okay, so this is power density of the real antenna divide with the power density of the references antenna. Okay, so D is a unitless. D is a gain is a unitless parameter. Okay, so the power density of real antenna here, this is actually we do a PD actually divide with PD references, where PD power density is power per unit area. Okay, power per unit area at a given point pada satu-satu tempat. Okay, pada satu-satu point dalam satu kawasan. Okay, and later you after that we also see that we also have power gain. Okay, so the power gain uh, same as directivity gain except that the total power fed to the antenna is used. Antenna efficiency is considered. So now we consider with the power with the antenna efficiency. So the power gain GP is equal to directivity gain multiplied with the antenna efficiency. Okay. So antenna efficiency, we have learned previously that the antenna efficiency is in terms of percentage. Okay. But remember when we want to multiply here, we need to make it as absolute value. Okay, between 0 until 1. So kalau for example like 75%, that means here we need to put 0.75, something like that. Okay, and we multiplied with the directivity gain. Okay, so so this is the concept of the gain. Okay, because when we want to consider the power gain, we will combine it with the input power P in. Okay, we're gonna see later that P in is paired with the power gain. Okay, P in ini power input to the antenna will be paired with the gain power gain of the antenna. Okay, power input kepada antenna akan didarabkan atau dipasangkan dengan power gain. Manakala untuk directivity gain, for the directivity gain, we used uh, power radiation, P radiations, that we paired with the directivity gain. Remember P direction, this one, later you're going to see that when we want to calculate the EIRP parameters, we're going to pair this P radiation with the directivity gain. So, kita sudah lihat sebelum ini bahawa we have two kinds of power. The first one is the input power to the antenna P in, and the other one is the P radiation, P rad. So P radiations is the power used to radiate away the electromagnetic energy in the free space. And P input, P in, is the power supplied to the antenna. Okay, so so when we want to use the gains, okay, apabila kita nak menggunakan gains, so the directivity gains is actually the gains used at certain directions towards the gains used towards a certain directions. Okay, that is why later that you're going to see that the directivity gain is going to be multiplied with the radiation power radiations so that we can know the total EIRP. Okay, manakala when we want to consider the power gain of the antenna, okay, it is related to the antenna efficiency itself and the power supplied to the antenna. Okay, so apabila kita nak mengukur EIRP juga berdasarkan power gain, dia juga mengikut uh, betul antenna efficiency berdasarkan parameter antenna efficiency dan juga power yang dibekalkan kepada antenna tersebut. So what's the relationship about that? We're going to see in the next topic about EIRP. Okay, effective isotropic radiated power. Okay, EIRP. Okay, so ini ada di dalam topik seterusnya. That one later, after a few slides later. And radiation pattern. So radiation pattern, it is a polar diagram of graph representing field strength of power densities at various angular position relative to the antenna. Dia menggambarkan satu field strength ataupun power density at a specific angle from the antenna. Okay, it is a diagram indicating the intensity of the radiation. Dia menggambarkan intensity kekuatan radiation yang dari kekuatan radiation antena yang dipancarkan pada satu-satu arah. Okay, so how does the antenna radiation patterns looks like? Okay, so it is look like this. This is the 3D radiation pattern. So ini bentuk 3D. So we also have a 2D radiation patterns, but 2D radiation pattern already been removed from the slides. 2D we also have 2D radiation pattern where it is also based on the angular, okay, angle 0, 180, 90, and 270. So the radiation pattern for 2D looks something like this. The antenna is at the center, for example. So we have the radiation patterns. Okay. So this is in this picture shows the 3D radiation patterns for the antenna. So you see that the antenna is located at the center. Okay, the antenna is located at the center, and we're gonna see where does the most of the power goes to. Okay, you see that the most of the power is radiated towards this side, on the right side. Okay, so sebahagian besar daripada power ataupun energy dipancarkan pada arah ke sana, ke sebelah kanan. In this case, let's say this is towards a 90-degree angle, for example. Okay, so sorry, towards a 0-degree angle over here, towards the x-axis like this. So ini kita lihat sebahagian besar daripada electromagnetic energy dipancarkan pada arah z-axis in this example. Okay, so this is what we call as the major lobe. Okay, major lobe shows the most intensities of the radiation from the antenna. Dia menggambarkan majority ataupun sebahagian besar intensity daripada gelombang yang dipancarkan oleh antena pada satu arah. So ini dipanggil sebagai major lobe. Okay, lobe yang paling besar. So lobe yang paling besar menunjukkan majority ataupun the most intensity towards that directions. Okay, so since this is not showing the angle, okay, normally it shows the angle. Okay, so here I just say that this is towards z-axis. Okay, and then we also have what we call as the side lobe. Okay, side lobe is actually somewhere on the side directions. Okay, we have a side lobe. It juga dipanggil side lobe. Side lobe is small intensity of the radiations is at the uh, is radiated at the sides, ke arah tepi dia di bahagian tepi daripada major lobe tersebut. Okay, so the intensity is smaller than the major lobe. Okay, dia punya intensity lebih kecil daripada major lobe. And then we have another one is what we call as the back lobe. Okay, this is the back lobe. So back lobe is the a small energy. Okay, it shows the small energy that has been radiated about 180 degree from the major lobe. Okay, lebih kurang 180 darjah daripada major lobe. So remember that gelombang, the energy, so the radiation is not only towards certain directions. Remember that when we transmit the signal in the free space, the signal, the electromagnetic energy will go in many directions. Okay, bila kita pancarkan dalam udara, dia sebenarnya tidak menumpu kepada satu arah sahaja, sebenarnya dia akan terpancar pada banyak arah. Okay, so that's why we want to see the patterns. Okay, majority will go to the side, to the major lobe, some goes to the side lobe, and very small amount will goes to the back. Back lobe ini dia punya intensity very small, very small intensities. And then about far field region. So far field region, here is the region what we call as the Fraunhofer region. Okay, so Fraunhofer region is the distance from the antenna. Okay, that when the power reach the Fraunhofer region, it will continue to radiate outwards and never return to the antenna. Okay, so remember that here is the antenna, for example, and here is the region of far field region. So remember that the antenna, the radiation patterns looks like this. Okay, so when the radiation, okay, when the signal goes more than the far field region, what happened is said that the signal will not radiate, will radiate outwards and never return back to the antenna. Okay, sebab dia punya bentuk pancaran ini adalah seperti gelombang spherical. Okay, and when it is closer to the antenna, you're going to see that some of the radiation is returned back to the antenna. However, when the signal is transmitted far away, far from the far field region, okay, far from the Fraunhofer region, it will not radiate backward. It will travel outwards towards the destinations. Okay, itu dia punya konsep of the far field region. Maknanya tidak ada gelombang yang dipancarkan, yang dipantulkan semula ke arah antena, dia akan bergerak terus ke arah receiver. Okay. So the radiation patterns, okay, radiated power is important. Antenna radiation patterns are generally given for the far field region. Okay, biasanya kita menggunakan radiation pattern adalah berdasarkan far field region. So we're gonna see later that the far field region, the distance from the antenna, okay, R is the distance from antenna to the point of the far field region, is equal to 2 times the diameter. D square is the diameter of the antenna, divide with lambda, 2d square over lambda. Lambda is a panjang gelombang which is related to the frequency. And then we have another one, what we call as a near field region. Okay, tadi far field, now is a near field. Near field region, also known as the Fresnel region. Okay, so near field region is a field pattern is close to the antenna. So this is the region that is very close to the antenna. Okay, kawasan yang berhampiran dengan antena tersebut. So the near field region is defined as the area with the distance 2d square over lambda from the antenna, where lambda is the wavelength and d is the antenna diameter. Okay, that means if you say that between antenna and here is the antenna, So the distance between this region, 2d square over lambda. So this is a near field. Okay. And then after this here is a far field. Okay, so we want to know this the distance over here. What is the distance here? So this is a near field, and then after the near field is a far field, because far field you see that here is larger than okay. Okay, this is to show the radiation of the antenna in the far field and also in the near field. Okay, so you see that 2d square over lambda is somewhere over here. Okay, and the antenna is over here. So between antenna and this area and this line is near field. Okay, this is near field, and over here is a far field region. More than 2d square over lambda. Okay, so you see that if you see from this picture, you're gonna see that it shows some of the radiations. Dia juga menggambarkan macam mana bentuk radiation itu. Ada yang color hijau, this green color, and this orange color, something like that. Okay, so you see that when it goes to the far field, more than the far field region, the radiation seems transmitted forward upwards and never returned back to the antenna. So that's the theoretical concept of the near field and also the far field region. Okay. Example. Find the far field distance for an antenna with a maximum dimension of 1 meter and operating frequency of 900 megahertz. Okay, so you are given a dimension. Dimension here is referring to the diameter. Okay, dalam kes ini dia merujuk kepada diameter. Diameter of the antenna, dimension of the antenna. Okay, so D is 1 meter, F is equal to 900 megahertz. So in order to find lambda, you need to do C over F. Okay, C over F, speed of light, divide with the frequency. Okay, so therefore the distance R, because you want to find the far field region, so it is 2d square over lambda, which is equal to 2d. D is 1. So you put inside the parameters, 1 meter for the diameter, given the dimension over here, multiplied with the frequency, this is F, 900 megahertz, divide with the speed of light, okay, kelajuan cahaya. So we're going to get 6 meter. Okay, so more than 6 meter. Okay, if more than 6 meter, that means it is the far field region. Okay, so this is the distance from the antenna, and after this distance it's gonna be far field region. And then the question asks, what about if we use different frequencies? Macam mana kalau kita gunakan frekuensi yang lebih tinggi, the higher frequency? Okay, so what's the far field region? Okay, so you see that when we use different frequencies, okay, 2d square 2d square over, okay, sorry, I think maybe I should explain about this. This is 2d square over lambda, because lambda is C over F. So therefore we're gonna do 2d square F over C. Ini saya harap pelajar tahu this is actually 1 over lambda. So that's why F over C. Okay, and you put inside the parameters, so you get the answer 6 meter. Okay, remember F over C is actually 1 over lambda. 1 over lambda is actually F over C. Okay, so that's why in this example it substitutes the 1 over lambda with F over C. Okay, so here masukkan, we put inside the frequencies 3 gigahertz. Okay, 3 gigahertz. So sorry, 10 gigahertz, 10 gigahertz of frequency. Okay, we put inside the 10 gigahertz frequency, divide times dimensions times 2, divide with the speed of light. So therefore we're gonna get the far field region 66.67 meter. So the higher the frequency, the further away would be the far field region. Lagi tinggi frequency, lagi jauh far field region daripada antena. Okay. Field intensity. Okay, field intensity here, field intensity and power density. Okay, so field intensity here shows about electric field and also magnetic field. Remember, we are using electromagnetic wave. Therefore, we have E field and also H field. We have the electric field, and also we have the magnetic field. Okay, and power density is the power per unit area. Okay, so now we want to see all of these parameters. Okay, so the field strength is the basis comparison with an isotropic radiator. So how do we want to calculate the E field, electric field? Okay, E here means electric field, medan electric. Okay, so it is equal to square root of 30 times P times G divide, square root of 30 times P times G divide with R. Okay, so where G is the gain of the antenna, so R here is the distance. Okay, R here is the distance from antenna to a certain area. Okay, pada satu kawasan. So this is the distance R. Distance from antenna. Okay, dia adalah menunjukkan jarak daripada antena ke satu kawasan. Okay, the unit is in term of meter. Of course, the unit is in term of meter. So here you see that when we want to calculate the E field, okay, so E, you see that here is P times G. What is P? What is G in this case? Okay, apakah nilai P? Apakah P? Apakah G dalam konteks ini? So I will rewrite again. So E can also be written as square root of 30 times P radiation multiplied with directivity gain multiplied with GD divide with R. Or you can also do like this. E equal to square root of 30 times P input, P in multiplied with power gain, GP. Both, this is divide with R. So both of these will give the same answer. Kedua-dua ini akan memberikan jawapan yang sama. Okay. So, okay, now we're gonna see about for isotropic radiator. What happened to the isotropic radiator? Okay, so from here, so this is E field equations. So E field equation you can rewrite again like this. Okay, and this the equation below here, this is for isotropic radiator. Okay, for isotropic radiator, remember for isotropic radiator, both gains are equal to 1. Okay, so you see that here GD equal to 1, GP equal to 1. Okay, this is the isotropic radiator characteristics. Ini adalah sifat-sifat isotropic radiator yang mana dia punya gains bersamaan dengan 1. So when the gains equal to 1, therefore the E field for isotropic radiator is equal to square root of 30 times P divided with R. So this P doesn't matter. It can be, okay, this P can be P input or P radiation. Akan menghasilkan jawapan yang sama. Okay, because both of these equal to 1. Okay. So we're gonna see an example later about this thing. So previously we see about E field. What about H field? So now we can see the relation between power, E field, and also the H field. E field is the electric field, H field is a magnetic field. Okay, so power density. ketumpatan power. Okay, power per unit area. Okay, remember power density is a power per unit area. Okay, and it is equal to E field multiplied with H field. So E field, the unit is in term of volt per meter. Okay, we already calculate from these equations. And then H field is calculated as ampere per meter. So when we calculate both of these, we get VA over meter square. VA is a power. Okay, voltage times current. VA is a power. So power per unit area. Okay, so this is uh, you're gonna see later that in another slides it's also use PD. Okay, dalam slide yang berikutnya dia menggunakan simbol PD, power density. So here don't be confused. This is a power density. Okay? This is the first equation for power density because we have a few equations for the power density. Okay, power density dia ada beberapa equations yang boleh digunakan. Okay, one of them is this one. When we have the E field, we have the H field, we multiply together and we can find the power density. Okay, so this is the first equation for power density. This is the second equation for the power density. This one, eh? This is the second equation of power density. Okay, so power density is equal to power multiplied with gain divided with 4 pi r square. So you see that 4 pi r square is the surface area of a sphere, spherical shape. Okay, so area kawasan, luas kawasan yang dimaksudkan di sini adalah luas kawasan berbentuk spherical. Okay, the area that we means in this topic is about the area in a spherical shape. Okay, so luas kawasan sfera. Okay, kalau kamu masih ingat belajar mathematics in the mathematics, luas kawasan a spherical area, the surface of the spherical, the area of a spherical area is equal to 4 pi r square. Okay, so r is the distance, okay, from the antenna. Okay, where antenna located at the center. Okay, antenna terletak pada center. Okay, so you see that maybe we can see from this picture. Okay, so you see that this is the antenna, and here we have a R1 for this the distance R1, and we have R2 the distance outer layer here. Okay, so the radiations theoretically follows the spherical shape. Okay, secara teorinya radiation pattern of antenna follows the uh, spherical shapes. Okay, we always use a spherical shape to show the theoretical concept of the antenna. Okay, the radiation patterns. Okay, secara umumnya radiation pattern of the antenna follows the spherical shape. Okay, dia dipancarkan dalam almost all directions. Okay, so in this case, you see that here from these equations, I can rewrite again. Okay, so it is can be written as PD is equal to P radiation multiplied with directivity gain divided with 4 pi r square. Or you can also write PD, power density, equal to P input multiplied with power gain, okay, multiplied with power gain GP divide with 4 pi R square. So boleh juga kita buat dalam sebutan ini Okay. So because we don't know what is this P, what is this G, so it is related to power radiation and also power input. The G, the gain is also related to the directivity gain and power gain. Okay. So I can say that this is the second equation of power density. And then what? And then power density is said to decrease proportionally with the inverse square law, with the inverse of the square distance from the source. Of course, power density becomes smaller uh, when the signal travels far away from the antenna. Power density ini dia semakin berkurang apabila jarak daripada antena bertambah. So this is about R square here. So you see that the distance from antenna. So the further away the distance from antenna, the smaller would be the power density. Okay, lagi jauh jarak daripada antena, maka power density itu menjadi semakin kecil. Okay, it is based on this equation actually. Okay, lagi besar nilai distance, jarak daripada antena ke satu tempat, lagi kecil dia punya power density. Remember that we actually want the power density to be as big as possible. Kita inginkan power density sebesar yang mungkin. Okay, because this is like a coverage area. Ini sebenarnya menggambarkan seperti coverage area of the antenna. Okay, remember that power density also shows to us that this is also related to the coverage area. So the smaller the power density, that means the coverage will be becomes weak. Okay, coverage itu menjadi semakin melemah. Okay, kita sebenarnya ingin power density to be as high as possible, sebesar yang mungkin. Okay, lagi besar, lagi bagus. Okay, the higher the power density will be the better the quality of the signals. Okay, so and then the third equation of power density, okay, related to the E and H field. Okay, so this is the third equations. I can say that this is the third equations. So power density is equal to E square divided with 120 pi. Okay, so 120 pi is not a magic number. This is related to the epsilon r, related to the free space material. This is related to the dielectric parameter. There's equations to calculate this one for free space. So the udara, when we use the air as the medium, transmission medium, because the air also has the dielectric constant. So when we calculate the dielectric constant, and there's an equation to calculate these things, and we get this one becomes 120 pi. So if you see from, it is not shown here, in the old slides, slide yang lama, slide kuliah yang lama, ada ditunjukkan macam mana 120 pi ini diperoleh. Okay, so if you want, you can Google about this, about E square over 120 pi. How we get the 120 pi, this is related to the dielectric constant of the free space. So you're going to get the 120 pi. Okay, so I can say that this is the third equation. So E square over 120 pi. Okay, and then what? Okay, this is to show the field strength. Okay, the strength of the signal. Okay, when with related to the distance. Okay, so here the antenna is located at the center, and you see that when we move towards R, okay, so we're gonna get area is power times gain divided with the area, and when we move further away until 2R, okay, until 2R, you're gonna see that the area becomes bigger. Luas kawasan menjadi 4 kali ganda, because it is a R square. Okay, so it is a 4 times. Okay, dia menjadi times 4. So the area becomes a times 4. 4 kali ganda lebih besar. And when we move until 3R, So the area becomes 9 times from the previous one. Okay, from A here. So luas kawasan menjadi 9 kali ganda berbanding jarak daripada R. So this is related to the what they call as the inverse square law. So the further away the distance, that means the intensity will be spread in a bigger surface area. Okay, maknanya apabila kita semakin jauh daripada antena, the power multiplied with gain will be spread in a larger area. Okay, power multiplied with the gain. Okay, this what we call is the power density is the power is spread in a bigger directions. So in a bigger area. So that's why you get the power density becomes smaller because of the area. The area becomes bigger. So power itu di spread kan, we spread the power in a bigger surface area. So here you're going to see that over here the power density becomes smaller. Okay, example 7. Example 7. An isotropic radiator is radiating 1 watt of power into the free space. Okay. Calculate the electric field intensity and power density at a distance 1 kilometer from the isotropic radiator. Okay, so you have the isotropic radiator. Remember, isotropic radiator radiates signal in all directions. Okay, so when it mentioned about isotropic radiator, remember another characteristic is about gain. GD equal to 1, GP equal to 1. Apabila kita menyatakan tentang tentang isotropic radiator, ada dua sifat utama. Yang pertama, isotropic radiator radiates the energy in all directions, and then the gain is equal to 1, both GD and GP. Okay, and the question said that how much is the electric field and also the power density. Two things. The question asks about E and also PD. So E field we can use here. Okay, sorry. So you are given here radiating power. Radiating power means that P radiation. Okay, radiation power. And then you are given the distance 1 kilometer. So remember 1 kilometer you need to convert into meter. So it becomes 1000 meter. Okay, so therefore E field is equal to square root of 30 times P times G divided with R. Okay, so 30 times P power radiations multiplied with G. So it doesn't matter G because both types of G equal to 1 for radiator. Okay, so square root of 30 times 1 times 1 divide with distance 1000 meter. So you're going to get 0.0055 volt per meter. Okay, so this is actually volt per meter. Okay, sebab dia tulis M minus 1, actually V over M actually. Okay, and then what? Power density. So power density, we can calculate the power density is equal to E square over R. Okay, uh, so E square over 120 pi. So 0.0055 square divide with 120 pi. So you're going to get 7.9577 multiplied with 10 power of minus 8. The unit is watt per meter square. So you see that if you use another equation, I believe you also will get the same answer. Okay, either you want to use a P times G divide with 4 pi r square. So you can also use this equation to find the power density. Okay, so G, if you want to use these equations, that means P is 1 multiplied with 1, gain is equal to 1, divide with 4 pi, R is 1000 square. I believe you will get the same answer. Okay, you boleh cuba. Okay, you will get watt per meter square. Okay, boleh cuba sendiri. Okay, if you have question to ask, you can ask. You can always interrupt my lecture. No problem. You boleh tanya soalan. Okay. So if you don't have question, I will proceed with example 8. Okay. So example 8, electric field intensity is given. So this is the E field. Okay, is measured as electrical field strength of an isotropic radiator. Okay, if the radiator is radiating 1 watt of power, so radiating power, so that means this is P radiation. Find the distance at which the measurement is taken. So you see that we have the antenna, okay, isotropic radiator antenna, okay, and at a certain distance, okay, we don't know the distance, how much is the distance. We find that when we measure the E field, we find the E field is equal to 20 millivolt per meter. So the question asks how much the distance. So therefore, we can find this using E field E equation. E field equation. Berdasarkan E field equation, kita boleh mencari nilai R. Remember that E field is equal to square root of 30 times P radiation times G divided with R. Okay, so if you want to find R, so you put it outside R. So R is equal to square root of 30 times P radiations time, this is actually GD sebenarnya. Okay, because P radiation we multiplied with directivity gain. But remember, both of it is equal to 1 for radiation. For antenna radiate, for radiator, for isotropic radiator, the both GP equal to 1, GD also equal to 1, because this is a isotropic radiator. Okay, so we multiplied this one, R equal to square root of 30 times P radiation times GD divide with E. So square root of 30 times 1 watt multiplied with 1 for the gain, divide with the electric field. So you're going to get the distance in terms of meter, 273.86. So this is the distance from antenna until the measured area, which is over here. So this is around 273.86 meter. Boleh So kalau if you have question, you can ask me, no problem. Okay. If there's no question, I will move to the next.
Doktor,
Yes, silakan.
nak tanya untuk GD tu kalau soalan diberi tu bukan isotopic radiator, jadi dia punya gain tu kira macam mana
Gain. Okay.
Ha,
Okay. If it is not isotropic radiator, you will be given the gain. Gain
value.
akan diberikan.
Oh, okay.
So you will be given either GP or GD. Okay,
Alright.
kamu akan diberikan maybe salah satu GP or GD. Okay, and then you can use in the calculation.
Baik doktor, terima kasih.
Okay, sama. And then example 9, a field strength of 15 millivolt per meter. So this is E field. Okay, E field is given 15 millivolt per meter. Is measured from an antenna with a gain of 1.5. Okay, calculate the field strength of an isotropic radiator. Calculate the field strength. Okay, calculate the E field if we use isotropic radiator. Okay, macam mana kalau kita gunakan isotropic radiator? So now the question said that originally we have real antenna. Okay, given the E field, given the antenna gain. Now, let's say we change it to isotropic radiator. How much would be the E field? Okay. So ceritanya macam ni. So the story is like this. So originally you are given the real antenna. Okay. So at a set, this antenna has again 1.5 G. And then the E field is 15. So E field is 15 millivolt at a certain distance. We don't know the distance. At this distance, the E field is measured as 15 millivolt per meter. Now the question is, if we use the same amount of E field, okay, kalau kita menggunakan E field yang sama tetapi antena yang berbeza, okay, so we want, let's say we want to have a same E field at a certain distance, but using different kind of antenna, isotropic antenna. So now, if we want to use a different antenna, isotropic, okay, and we want to achieve the same E field, sorry, oh, sorry, yeah. Okay. So now if we want to use a isotropic antenna, okay, how much is the E field that we can achieve? Itu maksudnya. Okay, how much is the E field that we can achieve using the same distance? The same distance. How much can we achieve the E field? Okay, remember for isotropic, the G will be equal to 1. And then for the real antenna, the gain will be 1.5. Okay, so in this case, don't be confused because it is not mentioned here whether this is a GP or GP. So we are not sure about that. Okay, and let's say that the same amount of power is used. Okay, let's say we are using the same amount of power. Okay, we are using the same amount of power. How much can we achieve the E field at the same distance? So soalan ini sebenarnya bertanya seperti ini. Asalnya kita ada antena, real antenna. The antenna has a gain 1.5, this one, and with a specific power. We don't know how much is the power. And at a certain distance, R, we measured that the E field is 15 millivolt per meter. Now, the issue is, what if we change the antenna, kita tukar antenna itu, but the power is still the same. We are using the same amount of power, we inject the same amount of power, or we radiate with the same amount of power, and at distance R, how much is the E field that we're gonna measure? Berapakah nilai E yang kita akan dapat pada jarak tertentu, pada jarak yang sama? Because we want to compare. Okay, we just change the antenna. Okay, so now there are two variables that we don't know. The power, we don't know how much is the power. The distance, we don't know how much is the distance, but we know about the gain. Okay, kita tahu tentang gain. Gain for the isotropic radiator is equal to 1. Okay, so now you see that based on E field, okay, so E is equal to 30 times P radiations times G. Okay, so dalam case ini dia menggunakan P radiations. Okay, so P radiations multiplied with G. So this is the general equations for the E field. Okay, so and then we rearrange the equations. Okay, so 30 times P radiation divided with R is equal to E over square root of G. Why do the equation do like this? Why do the solution do like this? Kenapa solution ini membuat? Why? because we don't know how much is this, we don't know how much is R. But we know how much is E, we know how much is G. So this square root of 30 times P divided with R will become variable. Dia akan jadi satu variable yang kita tidak tahu. But we know E over square root of G, we know. We can do. Okay. So so let's say A becomes E over square root of G. Katalah A bersamaan dengan E over square root of G. So A is equal to 15 divided with 1 over 5 equal to 0.122. This one. So actually, the A parameter, okay, this is A parameter for the real antenna is equal to 15 milli divide with square root of 1.5. So we get 0.0122. Okay. And now the issue is now we want to find the new value of E, electric field. Kita ingin mencari nilai electric field yang baru. Okay. So, uh, so now you see that as I mentioned previously, that we are using the same amount of power and we want to find the E field at the same distance. Okay, kita menggunakan P yang sama, P radiation yang sama, dan jarak yang sama. Berapakah electric field yang akan kita capai? So you see that uh, at the beginning, we don't know how much is the P radiation for the real antenna. We don't know how much is the distance. Okay, but when we rearrange the equation, we find that square root of 30 times P divided over R is equal to E over G. That means, kalau kita menggunakan ini, if we use square root of 30 times P divided with R. So if we use the same amount of power, we use the same distance. Okay, for any kind of antenna, okay, it is equal to E divided with square root of G. So now, when we change to isotropic antenna, apabila kita tukar kepada isotropic antenna, what happened is that gain is equal to 1 and we want to find how much is E. Berapakah E field? Okay, so therefore, E is equal to, okay, E is equal to A multiplied with square root of G. A multiplied with square root of G. Apakah itu A? A will be the constant value regardless of the antenna. Okay, dalam case ini. Okay, because A is actually representing by this one. Okay, square root of 30 times P divided over R. So A is a constant parameter. And now we want to find A parameter if we use a different antenna. Kita nak cari nilai A. Sorry, kita boleh, sorry, kita nak cari nilai E. We want to find the electric field parameter based on different value of G. So therefore, electric field is equal to A parameter multiplied with square root of G. Okay, so A is equal to, sorry, electric field is equal to square root of G multiplied with A parameter. Apakah A parameter? A parameter adalah bersamaan dengan square root of 30 times P, power divided with distance R. Okay. So you see that from here, maybe I need to erase. Okay, saya padam sikit supaya tidak confuse. So therefore, E field, electric field, is equal to A multiplied with square root of G. Because now we are using the isotropic antenna, isotropic radiator, the gain is equal to 1. So therefore, A multiplied with square root of 1, so we get 12.2 millivolt per meter. So we get the new E field. So you see that the E field for isotropic radiator is smaller than than the electric field that we when we use a real antenna. Electric field ini menjadi lebih kecil apabila kita menggunakan isotropic radiator disebabkan oleh gain yang bersamaan dengan satu. Okay, so when the gain becomes smaller because we change the antenna, therefore the electric field becomes smaller. Itu maksud dia. So kalau kita lihat gambar ini, when we see this picture below here, when we change to isotropic radiator, okay, with the same amount of power, with the same distance from the antenna, and the gain is equal to 1. So therefore, we get the electric field becomes smaller, which is 12.22 millivolt per meter. Okay. So ini boleh ada soalan nak tanya? So because this is we play around with the variables in this case, because the scenario is we use the real antenna first and then we change to isotropic antenna. We compare both of it. Okay, so you see that electric field menjadi kecil pada isotropic radiator because the gain is equal to 1. Okay, if you have question you can ask, no problem. Okay, if not I will move to the next example, example 10. Okay, okay, this example, calculate the power density 10 kilometer away, okay, of an isotropic radiator radiating power of 5 watt of power. So now we have isotropic radiator, okay, isotropic radiator, and it radiates P radiations equal to 5 watt, and the distance is 10 kilometer, which is 10,000 meter. So the electric field strength is found to become 3 times stronger if the radiator is replaced with the real antenna. So now if we use if we use a isotropic radiator, kita akan dapat E field. However, if we use a real antenna, okay, if you use a real antenna, so you see that if you use a isotropic, that means a GP is equal to 1, GP is equal to 1. So I want to erase this one. I want to redraw again. Wait. So the question said that if we use a real antenna, okay, with the same amount of P radiation yang sama, okay, at the same distance, 10,000 meter, we're gonna get 3E. So the question is, find the gain of the antenna in decibel, dBi. Okay, so the issue now is how much is the gain. We don't know how much is the gain, GD. We don't know. So we need to find it. Okay, so okay, back to the equations. Okay, so now we want to find the G. So the G can be found based on the E equations, berdasarkan equation electric field. Okay. Okay. So you see that from these equations, E field for the isotropic radiator is equal to square root of 30 times P radiation times GE. So divide with R. So we get here is 0.0012 volt per meter. This is for the isotropic radiator. Okay. And for the power density is not asked in the question. Okay, this is actually additional. Power density kalau ikutkan dalam soalan dia tak tanya pun sebenarnya. So I believe that this is just to show you about the power density. Okay, so the power density is equal to E square over 120 pi. So this is 0.00212. Sorry. So 0.0012, sorry, 0.0012 square divide with 120 pi is equal to 3.9789 multiplied with 10 power of minus 9 watt per meter square. Okay, so this is the power density, power per unit area for the isotropic radiator. Okay, so now, okay, I put line over here so to differentiate. Saya buat garisan di sini. So starts from here. Now we replace the isotropic antenna with the real antenna. Okay, it is said that when we use the real antenna, we can achieve 3 times E field of the isotropic antenna. Apabila kita gunakan antena sebenar, kita akan mencapai electric field 3 times higher. Okay, so therefore, 3E is equal to square root of 30 times P radiations times G. G in this case is directivity gain. Divide with R. Okay, so 3ER is equal to square root of, so R is over here, 30 times, square root of 30 times P radiation times GD. Okay. So therefore, the directivity gain, so dalam case ini, the gain that we find here is actually related to the directivity gain. Okay, gain yang kita peroleh di sini sebenarnya merujuk kepada directivity gain. Okay, because we are using radiation power. Okay, so GD directivity gain is equal to 3ER square divide with 30 P radiation. Okay, why this is square? Because based on this square root, because we want to remove square root, therefore we square the on the left side parameter. Bahagian sebelah kiri ini kita kuasakan 2 supaya kita boleh buang punca kuasa. Okay, and then from here we divide with P radiations. So put inside the values. Okay, so this is the E field. So 3 times the E field multiplied with the distance 10,000 meter, and then we square all of it. Okay, kita kuasa duakan semua sekali dan kemudian kita bahagikan, and then we divide 30 times P radiations. Okay, so remember that this real antenna is using the same amount of power radiation, and we want to measure the E field at the same distance, but we achieve 3E. Now the question is, how much is the gain of the new antenna? Itu soalan dia. Okay, so we get the gain is equal to 9. Okay, the gain is equal to 9. The question asks in decibel. So in decibel, it is equal to 10 log of 9. So we get 9.5424 dBi. So don't confuse. What is this dBi? dBi is dB isotropic. Decibel with respect to isotropic radiator. It is decibel, dia adalah decibel, tetapi dia adalah decibel with respect to isotropic antenna. Okay, dia juga adalah decibel tetapi merujuk kepada isotropic antenna. That's why you put I, small I. Okay, so don't be confused. This is decibel. Okay, dia adalah jenis decibel, but with respect to the isotropic radiator. Normally for the antenna gain, we use a dBi. So when you buy a electronic device at the shop, when you see the specification of the gain, you're going to see that especially if you buy an antenna device, a device that contains the antenna. For example, like a router or wireless router, for example. Contoh, when you buy the wireless router at the shop, And you read the specification of the wireless router, you see the antenna specifications, you're going to show a decibel, a dBi. Okay, decibel isotropic, decibel with respect to isotropic antenna. That is the meaning of dBi. Okay, biasanya untuk antena kita menggunakan uh, dBi. Okay. Okay, the next part, the next topic. Okay, so this one, if you have question, you can ask. If you don't have question, I move to the next topic about EIRP. Okay, EIRP. So EIRP is equivalent power that an isotropic antenna would have to radiate in order to achieve the same amount power density in the chosen direction at a given point as another antenna. So this EIRP actually we should put it at the front side. Okay, sepatutnya topik ini, slide ini diletakkan di hadapan because we already discuss about EIRP sebenarnya. Sebelum ini kita sebenarnya telah discuss berkenaan dengan EIRP. So uh, for me, I would rather put this slide at the beginning. Okay, so that easy for you to understand. But no, never mind. Uh, so now the issue is like this. EIRP is actually equivalent to power multiplied with the gain. That's the basic concept of EIRP. So it is said that if we have a real antenna, okay, this antenna has a power P in, or this antenna also have a P radiation, okay, and it has a GP. It has a GP. We don't know how much in GD. Okay, so okay, at a certain distance R, okay, we want to achieve the same amount of power density PD at this point. Sorry, I delete again. I delete. Okay, at distance R, we can measure the power density PD. Okay. Now the issue is EIRP is related to the isotropic radiator. Okay, so is it that like this? Kalau kita ada isotropic radiator, if we have the isotropic radiator, okay, so the issue now is how much is the power that we need in order to achieve the same amount of power density as the real antenna. Okay, so how much is the power that we need for the isotropic radiator in order to achieve the same amount of power density as the real antenna? So this is the concept of EIRP. EIRP we compare it with the isotropic radiator, where we measure how much actually the isotropic radiator needs amount of power in order to achieve the same amount of power density with the real antenna. Uh, so because in the isotropic radiator, the gain is equal to 1. Okay, GD equal to 1, GP is equal to 1. So the issue now is how much is the P in, okay, how much is the P radiation that we need in order to achieve the same amount of power density. That's the theoretical concept of EIRP. Perbandingan power multiplied with the gain with the real antenna and isotropic radiator. Itu dia punya theoretical concept. Okay, contoh dikatakan di sini, if a given transmit antenna has a power gain of 10, okay, the given antenna effectively radiates 10 times as much power as isotropic antenna with the same input power and efficiency. So you see that if the real antenna has a gain of 10, okay, that means This antenna, this field antenna will radiate 10 times higher than the isotropic antenna given with the same input power, okay, and also with the same input power and same efficiency. Ini contoh kalau ada real antenna mempunyai gain bersamaan dengan 10, maka ia dikatakan boleh memancarkan power 10 kali lebih kuat berbanding dengan isotropic radiator dengan syarat powernya adalah sama dan efisiensinya juga sama. So what is this actually? The strength of the power, the strength of the transmitted power, EIRP, is uh, equal to P radiations multiplied with GD, or P input multiplied with GP. Okay, okay. Sekejap. Um, Okay, sorry about that. Semua boleh dengar suara saya?
Boleh doktor.
Okay, so I continue again. So EIRP, effective isotropic radiated power, is equal to P radiation multiplied with directivity gain. So the unit is in term of watt. Or we can also write EIRP equal to P in, input power, multiplied with power gain. So the unit also in term of watt. And if you want to write in term of decibel, okay, dB, so EIRP is equal to 10 log power radiation multiplied with 10 log power radiation multiplied with directivity gain, or we can say that in decibel, EIRP is equal to 10 log P input multiplied with power gain. Okay, so EIRP is actually the power strength actually, power multiplied with the gain. Okay, the strength of the power. Okay, so either we want to use to write in term of watt, or we can write in term of dBW. Okay, and here if we look again at the power density is actually equal to EIRP divide with 4 pi d squared. D here is a R. Tadi kita gunakan R. So don't be confused. This is also R square. Okay. So the thing that we used previously, P radiation multiplied with GD or P input multiplied with GP, it is actually equal to EIRP. Okay. Dia sebenarnya akan memberikan jawapan yang sama sebenarnya. And then we divide with 4 pi R square. So we get the power density. So if the output power from the transmitter is used, so we need to use a conductor lines loss in putting the EIR. So we're going to see about this later. So kalau ada losses, so if we have, let's say we have, this is a transmitter, for example. This is the antenna. So if we have losses here, so this is the power. The power here is PT. Okay, and here is the GP. GP is GP is the antenna. GP from here, from antenna here we have a GP. So EIRP is equal to PT multiplied with GP. You need to divide with losses. So this is in term of what? So we're gonna see about this issue, losses issue later at the last maybe a few slides at the end. Kita akan lihat tentang isu ini ya. Okay, example 12. Example 12. A probe measured 2 microvolt per meter. So ini this is a E field, volt per meter, E field of field strength 200 kilometer away from parabolic antenna. So the distance is 200,000 meter. Okay, from parabolic antenna. So when we say the parabolic, this is the real antenna with a directive gain of 1000 and antenna efficiency of 0.85. Okay, so okay. Find the power gain. So we have here is GD. We have here is efficiency 0.85, or this we can say that this is a 85% efficiency. Okay, find power gain GP. So GP can be found based on the directivity gain and efficiency. Okay, so GP is equal to directivity gain GD multiplied with antenna efficiency. Okay, so this is this one, power gain. GP is equal to 0.85 efficiency multiplied with directivity gain. So we get power gain 850. Okay, 850. And then EIRP we can find based on here is P radiation is given. Okay, P radiation is not given in this example, so we can find so EIRP is P times G. So it depends whether you want to use input power or radiation power. And if we see the from here, we can find the power based on the E field equation. Berdasarkan persamaan electric field, kita boleh mencari nilai power uh, menggunakan EIRP dalam kes ini. So you see that here E field is equal to square root of 30 times EIRP. So this is actually P times G. So EIRP is equal to E times R. Okay, E times R divide with, so E times R square divide with 30. So we get 0.0053. So this is the EIRP. Okay, EIRP. So this is regardless of you use P in multiplied with GP or P radiation multiplied with GD. So you will get this the same answer. So berdasarkan persamaan electric field kita boleh mencari EIRP. And then the question asks find the radiated power and input power. So since we already get the EIRP, now we can find the P radiation and also P input. Barulah senang untuk kita kira. Okay. So P radiation is equal to EIRP divided with directivity gain. Okay. So we already know the EIRP from the previous question. Kita telah tahu nilai EIRP daripada soalan yang sebelumnya. And then we divide with 1000. Okay, so this becomes 5.3 microwatt. Okay, and then we can find the input power based on the previous obtained EIRP value, divide with the previous obtained power gain. Kita telah dapat dalam soalan yang pertama, the first question. Okay, so 0.0053 divide with 850. So we're gonna get 6.2 microwatt. Okay, so you see that what's the difference. Okay, so here if you see this is the transmitter, for example, goes to the antenna. Sorry. So here is P in, and the power used to radiate is a P radiation. Okay, so you see that the input power is larger than the radiation power. Okay, you see that the input power is larger than the radiation power. The difference here, you see that the difference of power has been dissipated by the antenna as a heat, maybe. Okay, sebahagian power telah dilesapkan oleh antena dalam bentuk haba. Okay, some of the input power has been dissipated as a heat by the antenna, and most of it has been radiated away as a P radiation, sebagai P radiation. Okay, and then the last question say that the distance of the probe if an isotropic radiator is used for the same amount of field strength. So now the issue now is okay. So initially we have parabolic antenna. Okay, we have a parabolic antenna, and we measure the distance at 200,000 meter. Sorry. We measure the distance at 200,000 meter, and we find the E field to be equal to 2 microvolt, 2 microvolt per meter. Okay. Now the issue is, okay, soalannya bertanya, if we change to isotropic antenna or isotropic radiator, okay, find the distance. Okay, we need to find the distance that we can achieve the same E field. Okay, soalan tanya, kalau kita tukar kepada isotropic antenna dengan power yang sama, Dan E field yang sama, berapakah jarak sebenarnya? Okay, remember for the isotropic radiator, the gain is equal to 1. Okay, GD1, GP also equal to 1. Okay, and here we use the same input power. Okay, sorry. We use the same input power. Okay, we use the same input power. Wait. We supply with the same input power. Okay, how much would be the how much would be the distance in order to achieve electric field equal to 2 microvolt per meter. Okay, kita ingin mencapai electric field yang sama, tetapi isunya sekarang berapa jarak yang akan diperoleh, berapa jarak yang kita boleh peroleh electric field seperti itu. Okay, jangkaan saya, my expectation is that the distance would be smaller because the gain is small, so I can achieve E field, the same amount of E field at a shorter distance. Saya punya jangkaan kita akan mencapai E field yang sama tetapi dalam jarak yang dekat kerana gain pada isotropic radiator cuma bersamaan dengan 1. Itu saya punya expectation. So now I want to calculate. Okay. So you see that when we replace with the isotropic radiator, okay. So here E field is equal to 30 times P radiations, actually times GD. GD is equal to 1. So it does not show here. Okay, sebenarnya ada darabkan dengan GD, tapi GD bersama dengan 1. Okay, so therefore, the distance is equal to square root of 30 times P radiations, actually multiplied with GD. GD is equal to 1 for the isotropic antenna, divide with the E field, electric field. So we want to see if we get the same amount of E field, berapakah jaraknya? Okay, so we calculate, we put the P radiations from here, same amount of P radiation. Sekejap, saya lukis sikit. Okay, so we use the same P radiations, same amount of power radiations. We don't know the distance, but we want to achieve the same E field, which is 2 microvolt. So when we calculate, we found out that the distance is 6,304 meter ataupun 6.304 kilometer. Okay, so when you calculate this, you're gonna get 6,304 meter, or it is 6.304 kilometer. So you see that, okay, kita lihat di sini kelas, dengan menggunakan isotropic radiator, hanya pada jarak 6.3, only at the distance 6.304 km, we achieve the same amount of E field, electric field, 2 microvolt per meter. Whereas if we use a real antenna, we can achieve that E field, the electric field, 2 microvolt per meter at distance 200 km. Lebih jauh. Yeah. So which one is better? Of course, the real antenna is better because we achieve the strong E field at distance 200 km. Kita boleh mencapai E field tersebut, E field sebanyak 2 microvolt per meter pada jarak 200 kilo. Maknanya electric field is very strong at 200 km. Whereas for the isotropic antenna, we only achieve the same amount of electric field but at distance 6 km. Itu dia punya perbandingan. That's the comparison that we see. Because a parabolic antenna, it radiates the signal at a specific angle. Kalau kita menggunakan parabolic antenna, it will radiate the signal at specific angle. So the strength is more focused compared to the isotropic where it radiates in all directions. Dia tidak fokus. It is not focused. Isotropic radiator radiates in all directions. It is not focused at certain angle. Okay, so that's why uh, the 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 radiation is spread in all directions. Okay, whereas for we if we use a real antenna, it is more focused. So that means that the strength is more focused. So that's why at certain distance focus, that means we achieve a longer distance. Okay, and the strength would be becomes higher. Okay, kekuatan dia menjadi semakin kuat kerana kita fokus pada satu arah tertentu. Berbeza dengan radiator yang mana dia sebenarnya dia memancarkan semua arah. Okay, dia spread in all direction, which is not focus. Actually, when we want to transmit, we want to focus at a certain angle. Kita tak nak transmit pada semua arah sebenarnya. We want to focus at a certain angle with the highest possible of strength, power strength. Okay, so now you're gonna see, do you see the difference? So this difference mainly due to the gain factor, disebabkan oleh faktor gain. Okay, perbezaan ini disebabkan oleh faktor gain. The higher the gain, the higher would be the E field, the higher would be the EIRP. Okay, so in this case, actually, the good thing is if we use the parabolic antenna. Kalau kita gunakan parabolic antenna, lagi baik kerana dia punya E field lebih besar. Okay. Okay, if you don't have questions, I will proceed with the next topic, example 12. Kalau tak ada soalan, saya akan teruskan untuk example 12. Okay. Okay, example 12. For a transmit antenna with a power gain 10, okay, you are given GP equal to 10, and the input power is equal to 1000 watt. So you see that here, this is a transmitter, here is an antenna. So here is a P input, power input to the antenna. GP is the antenna power gain for the antenna. GP is equal to 10. Okay. Determine EIRP. So EIRP is power multiplied with the gain. In this case, P input multiplied with power gain. So 10 times 100, so we get 1000 watt. And then we convert into dBm and dBw. Okay, so you see that the first question, EIRP is equal to P in multiplied with GP, so we get 1000 watt. So the question asks in dBw and dB micro. So when we want to use a dB watt, so that means 10 log EIRP. Okay, so 10 log 1000, we get 30 dBw. And then in terms of that dBm, dB milliwatt, so 10 log 1000 divide with the reference 1 milli. 0.001 is 1 milli. So when we want to get a dBm, we need to divide with the reference value 1 milli, because we want to find dBm. This is chapter 1. So we divide with 1 milli, so we get the answer would be 60 dBm. Okay, and then what? The question asks, calculate the power density 10 kilometer away from the transmit antenna. So you see that at distance 10,000, okay, at distance 10,000, how much is the power density? Okay, because the antenna radiates the signal. Okay, and remember the radiation patterns follows a spherical shape. Okay, so therefore when we want to find the power density, it is uh, equal to power multiplied with the gain divided with 4 pi r square, which is a spherical shape, the area of spherical shape. So in this case, we can find a P input, sorry, this one, so this is actually multiplied with GP. Okay. So uh, power density. So power density is equal to P input multiplied with power gain. So this is actually EIRP. Divide with 4 pi r square. Remember r you must put in term of meter. Okay, remember that. Okay, normal common mistakes by the students. Students tends to put kilometer, which is wrong. If you put 10 only, your answer will be wrong. Be careful, students. The unit for distance in here in this topic, the unit for distance r is in meter. Don't put kilometer. Remember, if you put 10, habis. Okay, so that one is a common mistake. Always happen in the final exam. So don't do like that, please. Remember, the distance must be in term of meter. Okay, so here is 10,000 meter. Okay, 10,000 meter square. So you're gonna get 0.796. So try use your calculator. Cuba. You need to try using your calculator so that you can understand about this. Okay. Okay. So we get this one. So 0.796. So what is the next question? So the next question asks, how much is the power density if we change to isotropic antenna with the same input power and efficiency? Uh, So now the question says that if we change the antenna, okay, kepada isotropic antenna, this isotropic antenna has the same input power, okay, and we want to measure the power density, okay, at distance, same distance. In this case is 10 kilometer. Okay, so we want to find the new power density. How much? Now, remember that for the isotropic, GD equal to 1, GP is equal to 1. This is the characteristic of isotropic antenna. Okay, isotropic antenna, the first characteristic is that it radiates the energy in all directions. The second characteristic is that the gain is equal to 1. Uh, so now we supply with the same input power. We want to measure the power density at distance 10,000 meter away. Okay, how much is it? Okay, so you see that here the power now is becomes a 1. So now say that the power density is equal to P input. We use the same input power, we supply with the same input power, and then we multiply with the gain. Gain is equal to 1 for the isotropic radiator. We divide with 4 pi r squared, same distance. So you see that we achieve power density smaller, 0.0796 microwatt per meter. Lebih kecil daripada yang sebelumnya. Okay. 10 kali ganda lebih kecil. Why? Because of the gain. Okay. So that means if we use an isotropic radiator, we're going to achieve a smaller amount of power density at the same distance, 10,000 kilometer away. Okay. So in this case, remember class, we theoretically we want to achieve a power density as high as possible, sebesar yang mungkin. The higher the power density would be better, the quality of the signal. That means our coverage area would be strong. Okay, compare if you use a isotropic radiator, the coverage strength is becomes weak. Okay, so kita perlukan coverage yang kuat. Okay. Okay, example 13. So I hope that you are not tired. Saya harap kamu tidak penat. Because we are we are doing calculations. So I'm expecting you to use your calculator to calculate. Press your calculator and then do the comparison. Okay. I want you to learn with your calculator now. Okay, so that you boleh terbiasa mengira. If you have questions, please ask me anytime. No problem. Okay. So if you don't have question for this, I will move to the next topic. Kalau tak ada soalan, saya akan teruskan. Okay. If you have question, please interrupt me at any time. No problem. Okay. And okay. Example 13. Okay. Example 13. For a transmit antenna with a radiation resistance R radiations 72 ohm and effective antenna resistance is 8 ohm. So what is this actually? This is actually referring to the previous slides. If you see from the previous slides about the antenna, regarding the antenna design with using the resistance, this one. Okay. So R effective is RE, R radiation is RR. Okay. So maybe we can redraw again. Maybe kita boleh lukis semula. Yeah. Example 13. So that means we can redraw the antenna to become like this. So this is RE. So this is RE. And then this, sorry. Okay, so this is RR. Okay, RR, this is RR. Okay. And then the directivity gain, okay, the GD, so GD is equal to 20. So the input power P in is equal to 100 watt. Right. So now the question is, the question asks, find the radiation antenna efficiency, radiation efficiency or antenna efficiency. Okay, find the value of efficiency. How to do that? So antenna efficiency, we can find using the resistance value. This one you can see from the previous slides. So I go back to the previous slides, okay, to show you the efficiency based on the this one, based on the resistance value. So antenna efficiency is equal to RR, radiation resistance divided with radiation resistance plus effective resistance. Okay, because we have two equations for the antenna efficiency. This is the sorry, this is the first, and the second one is which one? This sorry, this one. Okay. Either we want to use the power, or we can use the resistance values to find the efficiency. Okay, we want to use the gain also, we can use the gain. Okay, so I go forward to example 13. Okay, I go forward to example 13. So efficiency is equal to R radiation divided with R radiation plus R effective. Okay, so R radiation divide with R radiation plus R effective multiplied with 100%. So 72 divide 72 plus 8 multiplied 100%. So we get antenna efficiency 90%. Very good, 90% efficiency. The next question asks, how much is the power gain? Power gain we can find based on the efficiency multiplied with directivity gain. Okay, antenna GP, this GP is equal to GD multi, so 8. So this is actually GP. So don't be confused. Don't be confused. This is GP. Power gain is equal to directivity gain multiplied with efficiency. Okay, directivity gain is given in the question 20 multiplied with 0.9 from the efficiency. So we get 18. Okay, we get 18. So you see that power gain is smaller than the directivity gain in this example. And then you see that in decibel, power gain is equal to 10 log 18, which is 12.55 decibel. Okay, 12.55 decibel, dB. Okay, and then what? The question asks radiated power in watts, dBm and dBW. Okay, the question asks about P radiation. P radiation is equal to P input multiplied with efficiency. Okay, P radiation is equal to P input multiplied with antenna efficiency. So antenna efficiency is 0.9 multiplied with the P input 100, so we get 90 watt of P radiation. So in terms of dBW, so 10 log 90 watt, 10 log 90 watt, we get 19.54 dBW. In terms of dB milliwatt, okay, in terms of dB milliwatt, so we get 10 log 90 divide with reference value 1 milli. Okay, so we get here 49.54 dB milliwatt. Okay, the next question asks EIRP in watt, dBm, and dBW. Okay, so EIRP is equal to, remember EIRP, we have two options. Okay, EIRP is equal to P input multiplied with power gain, or we can also write EIRP equal to P radiation multiplied with directivity gain. We have two options. Okay, so in this example, it use P input. Okay, dalam example ini dia menggunakan P input. So in this case, EIRP is equal to, in this example, it use a P input multiplied with GP. So this is actually GP, so don't be confused. So P input multiplied with multiplied with power gain GP. So 100 watt, okay, 100 watt multiplied with 100 watt from the question is given the 100 watt. And then the question also give us, the question give us a GD. So we already find the GP. Previously, we already find the GP. In the second question, we already find the GP equal to 18. So here 100 multiplied with 18, so we get 1,800 watt of EIRP. Remember, EIRP has a unit of watt. Okay, jangan tersilap. Uh, don't don't just write 1,800. Remember, class, in final exam, I'll be a bit strict about these issues because in the test, I don't mind because some of you didn't write the unit, but I still give you the marks. However, in the final exam, I'll be more strict about this issue. So if you don't write the unit, if the parameter has a unit and you don't write the unit, that means your answer is wrong. Okay, please be careful about this. And then in dBW, we can find EIRP in dBW. It is equal to 10 log 1,800. So we get 32.55 dB watt. And then EIRP in dB milliwatt. So 10 log EIRP 1,800 divide with the reference value 1 milli. So we get 62.55 dBm. Okay, remember that the difference is 30. Perbezaannya ada 30. So if you have questions, please ask. Kalau ada soalan boleh tanya. No problem. If you don't have questions, then I move to the next topic. Okay. So the next topics, it contains more pictures. Ada banyak picture, example of antenna. So, so this is quite interesting. We're gonna see a lot of antenna design. So we have wire antenna, aperture antenna, microstrip antennas, array antenna, reflector antenna, lens antenna. Many types of antennas. Okay, banyak jenis antenna. So this is a wire antenna, example of wire antenna. Example of aperture antenna. Okay, pyramidal horn, conical horn, rectangular waveguide. This is a microstrip patch antenna. So for the patch antenna, you see that the patch is depending on the design of the antenna. So you see that here, the antenna is actually this one. This is the antenna. Okay. Whereas this one is what we call as a substrate. Okay. So we design the antenna on the substrate. Okay. And here you see that the antenna is circular design, circular shape like this. This is the substrate. So if you see, no, we in our faculty we also have a final year project to design the microstrip patch antenna. Ada juga saya lihat projek-projek berkenaan dengan patch antenna yang mana pelajar perlu design patch antenna. Doesn't matter about the shape. Shape can be any kind of shape. And that one, when the students are already designed the patch antenna, and then they need to do the measurement to find the antenna radiation patterns. Okay, but now since it is a COVID situation, uh, the best thing is that we can only do the design simulation. We cannot do the patch because if we want to do the development of antenna, we need to go to the lab. Okay, kita perlu pergi ke lab dan kita perlu buat proses uh, etching pada substrate tersebut sehingga kita dapat bentuk ini, and then kita buat measurement. And then this is a array antennas. Array antenna, for example, Yagi Uda antenna, aperture array, microstrip patch array, slotted waveguide array dan sebagainya. Okay. So Yagi Uda, this is the TV antenna for television. The old antenna yang dulu-dulu kalau if you see we put above the roof antenna yang berbentuk ini yang ada garis-garis ni this is what we call as a Yagi Uda antenna. This is the old generation that we when you use the analog television so we use a Yagi Uda antenna. Even now we use a Yagi Uda antenna, but if we use a Yagi Uda antenna, that means we need a decoder in order to get the digital channel. Okay, kalau kita nak dapatkan digital channel, kita masih boleh menggunakan Yagi Uda antenna, but we need to have a decoder, okay, to decode the signal so that we can get a digital channel. Okay, and then reflectors antenna. So this is a kind of reflectors antenna, lens antenna. This is the parabolic antenna. Okay. So the size of antenna is depending on the lambda. Okay. The size of antenna is depending on the lambda, where lambda is equal to C over F. Okay. So the larger the size of antenna, that means lambda will become bigger. That means that this antenna supports a low frequency. Okay, antenna ini dia boleh support low frequency. That's why the size is much bigger. You see that if the frequency is higher, lambda will become smaller. The good thing about lambda, if lambda is smaller, that means we can design a very small antenna, like in your mobile phone, for example, because we use a high frequency. Okay, we use a GSM frequency or LTE frequencies, which is in 900 mega towards gigahertz. So that's why we can design a very small antenna inside the mobile phone. Okay, so kita boleh gunakan mobile phone yang kecil yang nipis So that's why the design of antenna becomes smaller when you use a higher frequency. So this is what the bigger the size, we use lower frequency so that we can transmit at longer distance in the ionospheric air. In the ionospheric layer, we can transmit the lower frequency signal. So ini biasanya untuk television punya uh, channel television channel. Helix antenna. So helix antenna also used for the satellite signal reception. Okay, satellite signal reception also can be used with helix antenna. Okay, parabolic antenna also can be used, like your Astro, for example. Astro, you use a parabolic dish. If you use a Astro, we use a parabolic dish to capture the signal from satellite. Okay. Another thing is that we can use a helix antenna also for satellite signal reception. Okay. The horn antenna. Okay, horn antenna can. This is for the normally for the point-to-point communications. We use a horn antenna. Loop antenna. This is a microstrip patch like the previous picture. Ini kalau gambar berwarna untuk microstrip patch antenna. So this is you see that here. This is the antenna. Okay, this is the antenna, and the brown color is the substrate. Okay, similar with this one. Okay, this is the point source, the input to the input of the antenna. Here is the you see this is the antenna. This is the antenna patch antenna. So the antenna design, we have many types of design depending on the application that we want to use, depending on the frequency that we used. Okay, so we can do a different kind of design in order to achieve a specific gain that we want for that application. Okay, kalau kita lihat antena design ni dia pelbagai kenapa perlu ada banyak sangat design? It depends on the frequency, it depends on the gain that we want to achieve, and also it depends on the bandwidth that we want to achieve, depends also on the application that we want to use. So dia ada pelbagai faktor yang menyebabkan design antena itu pelbagai. Okay. So radio wave propagations. Okay. So radio wave propagations, this is the characteristics of the radio wave. So this is the third topics of chapter 5. So kita dah masuk topik yang ketiga dalam chapter 5, iaitu berkenaan dengan radio wave propagations. So you see that radio waves, we have electromagnetic waves, types of electromagnetic waves can be divided into a few types. Radio waves, this is for the communications that we all use for AM, FM. For the digital communication also we use radio waves, okay, from a few megahertz until a few gigahertz. And then infrared, ultraviolet, X-rays, gamma rays. So we don't use we don't really use this for the communication, ultraviolet, X-rays, and infrared. We use it for the higher frequency. Okay, so this is for short distance infrared. Wave attenuations. Wave attenuations is the wave attenuations in this case is the ratio of two different power densities. Okay. Power density at the further distance divide with the power density of the shorter distance. Okay, dia adalah perbandingan antara power density pada jarak yang jauh dengan power density pada jarak yang dekat. So this is actually based on the picture. Wait, this is actually based on the picture of this one. Saya nak tunjukkan. So I go back to the previous slides. Just want to show you that this one. Maybe I so it is the ratio of power density at the outer layer R2 divide with the power density at the inner layer. Okay, so we do the comparison, we do the ratio, okay, the friction ratio in order to find how much is the attenuation, how much is the perlemahan signal yang berlaku when we move from a shorter distance to the higher distance, to the further away. Berapakah perbezaan antara nisbah tersebut because the power density at the inner layer is much stronger compared to the power density at the outer layer. So when we divide these two parameters, we're gonna see the friction of difference in terms of attenuation. Kita boleh melihat dia punya perlemahan signal tersebut. Okay. So this is you see that so the power density at the inner layer is much stronger compared to the power density at the outer layer. Okay. So here you see that power density at the outer layer divide with the power density in the inner layer. So P radiation, here you see that this is R2 outside layer. So you see that here. So this is R1, this is R2. R2. So you see that power radiation divide with 4 pi R2, 4 pi R2 square, and then divide with power radiation over 4 pi R1 square. So this is actually you need to divide with, you need to multiply it with G. So actually di sini ada G lagi sebenarnya. But since the G is the same, so we can cancel out the G. Even the power also can be cancelled out. So at last, we get a P radiation equal to the ratio is equal to R1 over R2 square. You see that R1 is below here. So mathematically, we can, when we divide this one, it becomes, this one becomes at the top and R2 becomes the denominator. So R1 over R2 square. Okay, dia bila kita bahagi, dia akan naik ke atas. So dia akan jadi, saya lupa apa nama dia. Bawah adalah denominator, atas adalah pengkali. So you see that the ratio is P1 over P2. It's called as the P1 over P2 is called the wave attenuation. So this is actually PD1. So don't be confused with power. This is not power. This is power density. So PD1 over PD2 sebenarnya. So uh, wait. So if I do like this, you will confuse. Okay. So power wave attenuation is actually the ratio of power two different power densities. That's it. Okay. Supaya lebih mudah untuk faham. Okay. So here you see that because of the attenuation due to the spherical spreading of the wave, it's sometimes called as a space attenuation. So with this is also known as the space attenuation. Why space attenuation? Because it is related to the space, related to the area. Okay, the further away the distance, the power density will become smaller. Okay, so attenuation here indicates that the energy has been spread out. Okay, if we move further away, that means the energy will be spread out in the bigger area. Okay, so it does not mean that the energy is lost. Dia bukan disebabkan oleh losses sebenarnya. Energy becomes the power density becomes smaller not due to the distance. Not due to the losses. Okay, power density menjadi kecil not because of the distance, not because of the losses, but it is actually due to the distance. The distance farther away, that means the spherical shape becomes bigger. So the energy is spread in a bigger area, bigger space. Itu sebabnya dia punya power density menjadi semakin kecil. Okay. So the wave attenuations can also be expressed in terms of decibels. So 10 log power PD. So this is actually PD2 divided with PD1. Power density at the outer layer divided with the power density at the inner layer. So it is equal to 10 log R1 over R2 square. Okay. wave absorption. So this is the characteristics of the wave. This is wave absorption. Wave absorption means that okay, so when the wave travel in the air, okay, the air particle will absorb some of the energy from the signal, and at the end it becomes attenuations. Dia akan menjadi lemah. Okay, because the air particles, okay, because in the air we have the particles in the air, it will absorb energy signal. Sebahagian tenaga, sebahagian energi daripada signal itu akan diserap oleh partikel pada udara. What are the main particles in the atmosphere? So one of the things that we can see here is the rain attenuations. Uh, wait, One of the things that absorb the wave energy is the rain particle, hujan. Okay, salah satunya adalah hujan. And then about dan juga partikel-partikel udara sebenarnya dia ada menyerap tenaga gelombang ini, energy of the wave. But the most critical part here is about rain attenuation due to the rain particles, raindrops. Okay, one of it, salah satunya adalah partikel air hujan. Okay, so that's why in the heavy rain, you see that the signal becomes weaker, especially if we operate at higher frequency. Kalau kita menggunakan frekuensi yang besar, maka dia akan lebih prone kepada rain, hujan, rain attenuations. Why? Why is it like that? Because if we use a frequency higher than 10 gigahertz, especially if we use a frequency higher than 10 gigahertz, so the signal is more prone towards the rain attenuations, towards the raindrops. You see that here, the lambda becomes smaller. Lambda menjadi kecil disebabkan oleh frekuensi yang besar. Okay, so what happened is that the wave becomes smaller than the size of raindrop. Saiz titik air hujan menjadi lebih besar daripada panjang gelombang tersebut. Remember that the lambda is also defined as how much is the distance that the wave has traveled in one complete cycle. So apa yang berlaku apabila size apabila when the lambda becomes smaller than the size of the raindrop, that means the raindrop can absorb a lot of energy from the signal. Okay, dia akan absorb a lot of energy. Okay, so that's why especially for the longer distance, the signal becomes attenuates and maybe it will not reach the destination. Contoh, example is like your Astro channel, Astro TV. You see that your Astro television, during the heavy rain, there's no signal. Okay, so we get angry at the Astro. Kita marah pada Astro. Kenapa tak ada signal during the heavy rain? It is not due to the Astro itself. It is actually due to the rain actually, because the satellite frequency is larger than 10 gigahertz. Okay, so that's why during the heavy rain, the attenuation becomes larger. So that's why the signal from the satellite unable to reach your home when the raining is heavily. When the rain is heavy, there's a lot of attenuation happens. So that's why the signal unable to reach at your home. So that's why you cannot watch the television. Okay. So in Malaysia, especially, we have a higher volume of raining. So it is not really suitable for the satellite communication actually, because we operate at gigahertz frequency. So it is not viable. It is not really good, especially in Malaysia, because we have a lot of raining. We need to think of something else uh, to help the signal become stronger. Okay, maybe operate at lower frequency a little bit compared to the higher frequency. So you see that wave absorption not only due to the rain particles, it can also due to the oxygen particles and water vapor particles. So dia ada dia punya absorption uh, the absorption level based on the dB per kilometer and also based on the frequency. So the higher the frequency, you see that the absorption becomes higher. Okay, regardless of the type of particles, tidak kira jenis partikel apa pun, apabila kita operate pada frekuensi yang tinggi, when we use a higher frequency, the absorption becomes higher. Okay, the absorption becomes higher. Wave refraction, pembiasan. Okay, so we have learned about refraction, pembiasan. I think maybe during your secondary school, you learn about pembiasan, refraction. Refraction is when the wave travel at different medium, okay, with a different density. Okay, when the wave travel at different medium, so medium one, medium two, has a different density. What happen is that the wave does not pass through at a straight line. It will bend. Okay, it will bend towards a different directions. Okay, so this is what we call as a refraction. So medium one has different density to medium two. In this case, in my example, medium two has a higher density. So the wave will bend the directions and not going straight line like that. Okay. So this is related to the Snell's law. If you remember the Snell's law, so ini adalah uh, this is the phenomena of refraction. The wave will bend at the different directions if the wave travel from one medium to another medium. Okay, so this is related to the Snell's law. Reflection is pantulan. So when the signal travel at different medium, medium one, medium two. So here you see that the incident angle is at certain angle, theta. What happen is that the signal will reflected back. Okay, the signal will be reflected back. So in this case, we are not talking about straight line. It must be at certain angle. Okay, dia perlu pada certain angle. And due to the difference in terms of density, so this wave will be reflected back completely. Okay, so this is a reflection. Okay, diffraction, serakan energy, penyerakan energy. So this is defined as the redistribution of energy within the wavefront when it passes near the edge of an opaque object. Okay, so it is a phenomenon that allows radio wave to propagate around the corners. Okay, so you see that here what happened during the refraction is that when the wave travel in these directions, you see that so we have the opaque object, we have a hollow over here, and what happened is that the energy will be redistributed to be like this. Okay, the wave energy will be redistributed. And also when the wave travel hit the edge of the object, apabila gelombang itu melanggar bucu objek, okay, the edge of the object. So what happened is that the signal energy will be redistributed. Dia akan berubah distributionnya. Itu this is a diffraction, serakan gelombang. Okay. Interference is when two radio waves have a same frequency. What happens is that it will cause interference from one channel to another channel. Akan berlakulah gangguan signal yang mempunyai frekuensi yang sama. So for example, if you transmit at 100 megahertz, I also transmit signal at 100 megahertz. So what happens is that your signal and my signal will mix together. So what happens is that at the receiver side, the receiver will be unable to differentiate. So is this my channel, this my signal or your signal? So this interference, what happens is that the receiver will be unable to demodulate the original signal. Okay, kesan daripada interference ini mengakibatkan receiver gagal untuk melakukan proses demodulation untuk mendapatkan signal yang asal. So the receiver will be unable to differentiate which signal is this from. Okay, dia tidak dapat nak membezakan. So we try to avoid the same frequency. So that's why in the communication system, we divide each channel as a different set of frequencies. Okay, setiap channel yang kosong itu dia mempunyai frekuensi yang berbeza-beza. So we can use any available frequencies. So we try to avoid same frequency. Kita cuba untuk mengelakkan transmit pada frekuensi yang sama. Otherwise ada interference. Okay. Free space loss and phase transmission. So this is the very important topics for the final exam. Okay, so you need to listen carefully about this. So since we have only 20 minutes remaining time, so maybe I need to explain. I hope I can explain some of these topics before we can continue next week. So here you see that we have transmitter. The power emitted by the transmitter is power PT, power transmit. And then here we have transmission line. Transmission line has losses, LT, losses. And then the input to the antenna is P input. Some of the power will be losses, will be dissipate. Most of the power will be radiated as a power radiation. And here we have GT, gain of the transmitter antenna. Okay, so this is gain of the antenna, GT. We just put a GT. It doesn't matter this is a GD or GP. Later you're gonna see the difference. So ini kita anggap sebagai general gain of the antenna. And then EIRP, power multiplied with the gain. Okay. And then at a certain distance, we get a power density, power per unit area at the receiver side. The gain of the receiving antenna is GR. The output power here is P out. And here we have the losses at the receiving line. And the power received by the antenna is PR. Okay. So this is EIRP. We already know about EIRP. So EIRP is P in multiplied with GT. Okay, P input multiplied with GT. So what is power density is equal to P input multiplied with GT divided with 4 pi d square or 4 pi r square. R is the distance. Okay, where is R?
Doktor,
Yeah.
GT tu bukan GD directive gain. Kenapa dekat sini dia tulis GT
GT here means transmitter gain.
Oh, transmit. Oh, dia tak sama dengan directive punya gain yang sebelum
So
ni.
if you see from here, this is actually GP actually. Ini sebenarnya GP. Okay, this is actually GP.
Bukan GD
P input, you see that P input we multiplied with GP, P radiation we multiplied with GD. Okay.
So sekarang yang guna tu GP bukan GD.
Yeah, GP.
Right.
But normally when we give the questions, kalau kita berikan soalan, we just put antenna gain. Okay, that means it is a G transmit. GT here means G transmitter antenna. Gain of the transmit antenna. Kalau GR is the gain of the receiving antenna.
Baik, doktor.
Okay. So where is D? D is the distance. This is the distance. Okay. D or R. You can put D or R, no problem. D or R in meter. Okay. And then what? Amount of energy captured depends on the gain of the received antenna. The output of the antenna P out is equal to, where is P out? P out is the power output from the receiving antenna. So P out is equal to power density multiplied with the AE, effective area of the receiving antenna. Okay, normally in the question we give the same antenna, transmit antenna and receiving antenna has the same characteristic. Biasanya kita bagi antenna jenis yang sama. So tidak ada dalam in that case, if you see from the previous questions, the transmit antenna and the receiving antenna are the same. That means the gain are the same. Okay, untuk memudahkan pelajar biasanya kita bagi yang sama. Okay, so you need to know that the P out is equal to power density multiplied with AE. Power density we already calculate from here. So P in multiplied with GT divided with 4 pi d square multiplied with AE. AE is the receiving antenna effective area. What is AE? Okay, AE is related with GR. Sorry, AE is this one. AE is square root. Sorry, AE is antenna efficiency, receiving antenna efficiency multiplied with actual area of the receiving antenna. Actual area. So this is depending on the dimension. So normally, if a parabolic antenna, we use a pi r square. Okay, because we assume that the area of the antenna is a circular shape. Ni kalau parabolic antenna. So because in your syllabus we use a parabolic, that means the surface area of the antenna is a circular shape. So it's a pi r square. Okay, so and this is the antenna efficiency. Okay, so therefore GR is equal to 4 pi AE over lambda square. So this is a given equations for GR. So from here we can find the AE. So AE related to GR. Okay, we can also do AE like this. AE based on efficiency multiplied with the area, but we want to relate with the GR. Kita nak relatekan dia dengan GR. So therefore, effective area of the antenna, of the receiving antenna, is equal to GR multiplied with lambda square divided with 4 pi. Okay, so we can put into the equation, into the previous equation. Kita boleh letakkan dalam equation yang ini. So what happened is that it become like this. Okay, P out is equal to PD multiplied with AE equal to P in multiplied with GT divided with 4 pi d square. Sorry. And then multiplied with, this is AE. This is AE. So what happened to the equation? It will become like this. P out is equal to P in GT GR multiplied with square in bracket lambda over 4 pi d square. So this is the general equations for the P out. Di mana P out? Again, P out is here. So you need to understand about this. So P out is the output power. P out is the output power from the receiving antenna. Dia adalah keluaran daripada receiving antenna. So we get this P out. Ini belum PR lagi because later we need to subtract with the losses over here. Okay, so now we get the P out. Okay, P out equal to P in multiplied GT multiplied GR multiplied with lambda over 4 pi d square. So this is also known as the Friis equation. Friis equation. Okay. So the last equation, also known as a Friis transmission equation, and from the basis of radio propagations, so dia dipanggil sebagai Friis transmission equation. Okay, so this is a Friis transmission equation. So if you want to Google, you can search for Friis transmission equation. So this is the equations. And the last term, okay, this term, lambda over 4 pi d square, is known as the free space loss, also known as the FSL. Short formnya adalah FSL. Okay, so this is the losses due to the distance. Okay, this is what we call as the attenuations. The losses due to the attenuations. Okay, so this is FSL is always happen. Dia mesti ada. Okay, in the Friis transmission equation, FSL will be there. Okay, that means that the losses due to the distance, it will always be there. Okay, dia mesti ada dalam ni, disebab losses yang disebabkan oleh distance dan juga frekuensi yang digunakan. Okay, so therefore it is sometimes more convenient to inverse the equation so that we get the decibel value be positive. So if you see that this FSL, if you convert into decibel, you're gonna get a negative value, negative dB. So what we want to do is that we inverse this equation, so it becomes a 4 pi d over lambda, so that we can get positive dB. Okay, so this is not we just want to get a positive value so that easy for us to do the calculation. Okay, this is no problem. Kita cuma nak dapatkan dia dalam bentuk positive value. So this is the explanation. In dB notation, positive number greater than 1 will give you positive value dB. For value greater than 0 but less than 1, dB is negative. So no dB value for negative number. Uh, so 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 that's why we reverse the FSL equations to become 4 pi d over lambda. Okay, so ini tidak ada pengubahsuaian terhadap value. Dia tidak mengubah value sebenarnya. Kita just reverse so that easy for us to do the calculations only. Okay, when we speak about FSL, how much is the FSL? We need to give a value, not the negative value. We need to give a value, something value. Because if we do like in these terms, we're gonna get a negative value. So it is not the suitable way to convey the value. So cara yang betul adalah kita terbalikkan dia, and then we do the 20 log. Macam mana dapat 20 log? Because here we have a square kuasa 2, so it becomes 20 log. Okay, so therefore FSL is equal to 20 log 4 pi d over lambda. So here you're going to get positive decibel. Okay, so so here, okay, so ini sama macam tadi. So this is actually the same as if you do P input multiplied GT multiplied GR multiplied with lambda over 4 pi d square. Ini sama lah. Okay, sama. So if you want to divide, that means it becomes you put in the log and the denominator. Ini sama. So jangan confuse, ini sama. Sama seperti ini. Okay, dia letak di bawah, dia bahagikan, and then so it becomes like this. So therefore, the final equations, become like this in decibel. Okay, the final equation become like this. So you see that here, this is also the final equation. Okay, jangan confuse. This is the final equations. Okay, in watt, but when we want to calculate in decibel, okay, when because it is more easier to calculate in decibel, lebih mudah untuk calculate secara dalam bentuk decibel. So therefore, P out is equal to so P in. So it depends, class. If this is a dBW, that means a P in dBW. Okay. This one is dB, this one is dB, this one is dB. Okay, so you see that here, all the plus over here is the power minus with the losses. So this is actually the losses part. So that's why we use a negative. So negative here actually because here we divide. Sebenarnya kalau kita bahagi dia akan jadi negative. So that's why actually the negative parts here also shows about the losses. Okay. And let's say we have losses at the transmission line, LT and LR. Katalah ada losses, katalah. Okay. So now we see losses, LT and LR. Yeah, sikit lagi, sorry. Okay. So what if we have LT and LR? Okay, LT and LR. That means we need to put inside the equations another types of losses. FSL is mandatory. Okay, LT and LR depending on the whether there's a losses in the line or not. Okay, so if there's a LT and LR, that means we can put inside the equations. Okay, so therefore PR. So now we can calculate PR, receive power at the receiver. Okay, because we include the LT and LR. So this is phase transmission equations. We multiplied with the another losses from the transmission line. Okay, this LT is the losses at the transmitter transmission line. LR is the losses at the receiver transmission line. Therefore, PR, power received at the receiver, okay, power received at the receiver is equal to so this is if we put here dBW, this is dBW, this is dB, this is dB, this is the FSL also in dB. Okay, this is FSL. This is also dB, this is dB. So you see that this is the power multiplied with the gain, and this is also the losses part. So we minus all the losses. So we get here dB. Okay. So you see that class, P out and PR, it is related. So this this P out can also be PR. Okay, dia akan menjadi PR if if L, T and LR equal to 0 because there's no other losses here. Okay, so P out can become PR. Okay, if the losses LT and LR is equal to 0. Tidak ada losses pada transmission line. So dia terus diterima oleh receiver. P out tadi I repeat again So P out can becomes equal to PR if there's no losses in the line. Kalau tak ada losses, dia terus diterima oleh receiver. There's no other losses. For example, okay, if the losses only due to the FSL, that means the P out directly received to the receiver. And this is very important and it will come out in the final exam. So I will explain this example in next week. Sudah tak ada masa, so ada lagi 2 minutes. Sorry about that. Okay. So the last example is very important for your final exam. I will explain next week. Maybe next week we're gonna have maybe 1 hour class, and then you can discuss with about your project. Okay. So that's all for today until this one, until freeze transmission equation. Okay. So we can scan the attendance. Sorry, I'm late. Saya lambat sikit, sorry ya. So semua boleh on you punya reader, you punya QR code reader. So we can so So after scan your attendance, you can go out from the class and move to another class. Okay, no problem. So here, sorry about that.
Doktor, saya tak boleh nak scan, doktor.
Tak boleh nak scan, sekejap eh.
Okey, okay.
Nama siapa?
Muhammad Syarul Nizam bin Mustafa.
So better you
Muhammad,
try to scan. Kenapa tak boleh scan? Sekejap eh.
sebab saya, doktor.
Okay, tak apa. You tunggu dulu. Yang ada yang boleh scan, sila scan eh.
Okey, okay, doktor.
Sekejap eh.
Doktor,
Ya.
nak tanya untuk projek tu kan, ada presentation live dengan doktor ke or just video presentation saja?
Akan ada both.
Oh, akan ada dua.
Ada video dan juga nanti akan ada macam sesi tanya Q&A lah. Saya akan tanya sikit lah. Maybe saya plan macam nak buat masa study week untuk Q&A tu. Just maybe maximum 15 minutes. 15 minutes maximum. Just maybe kita akan buat time slot untuk setiap group ada time slot je. So you just online pada masa tersebut and then saya cuma bertanya apa yang you buat bla 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 and that's it.
Oh, tak payah nak present the slide lah.
Oh, tak perlu slide. Slide you tak perlu, you boleh buat video nanti sebenarnya demo video.
Maksudnya video tu tunjuk dekat doktor ke masa present tu ke macam mana?
Sebelum tu you boleh dah upload video dululah.
Doktor, satu lagi.
Okay,
Banyak pula soalan saya.
silakan.
Untuk video tu, ada introduction macam which is macam
ada apa konten dalam video kami yang
saya nak tanya konten dalam tu lah.
Ya, nanti saya maklumkan boleh.
Boleh
Lepas tu,
doktor.
doktor, saya nak tanya pasal report punya contents tu, doktor ada boleh bagi tak yang format tu sebab kita orang nak follow itu rubric.
Ya. Saya belum bagi lagi final rubric.
Setakat ni doktor bagi progress 2 dulu baru.
Jadi
after this I will give you the rubric for the final report and also for the final demo. No problem.
Jadi doktor,
Okay,
saya nak
doktor.
tanya untuk minggu ni punya video progress yang tengah hantar dalam outer tu, which is yang demonstration about the GUI layout saja ke ataupun overall?
Just the progress. Because I'm expecting you not completely finished. I'm expecting you around 90%, for example. So you just see what you have.
In the video just only consists of the layout of the GUI
Ya.
Yang lain intro dengan conclusion dengan lain punya content tu tak perlu attach together lah.
Tak perlu.
Okay.
Cuma follow the rubric, situ ada pasal minutes of meetings and so on. Cuma masukkan yang itulah. Dia ringkas saja.
Yang minute of meetings tu itu untuk progress report, tapi untuk video presentation punya rubric tu doktor belum bagi tahu. Jadi
belum.
jadi kita
I will give you
nak
this week as soon as possible. I will give you the rubric for the video for the demo and also for the final report. Saya akan tuliskan dulu.
Okay doktor, thank you.
Sorry lambat sebab
baik.
Saya perlu penyelaras resource because we will use the same rubric from the previous semester. However, the previous semester the project is different, so we need to adjust the rubric. I will give you saya akan berikan masa yang panjang, so don't worry.
Jadi doktor, saya nak tanya untuk video yang kena submit dalam minggu 13 tu, ya demo tu semua orang kena ada dalam video ke macam mana ya? I mean satu group satu orang untuk show itu UI layer ataupun semua orang kena buat satu Google Meet dan tunjuk benda tu and then explain benda.
Make a video because later I akan buat sesi macam Q&A. So Q&A semua member bertanya lah. But for the video, I'm not expecting you to show your face everyone.
Doktor means like we just buka itu laptop then guna MATLAB simulation untuk display sajalah. Tak perlu show face dengan
You need to explain how you design the GUI from the beginning until the end. So that means you boleh buat macam live video. So you boleh buatkan video tu
So contoh lah
awal
doktor.
sampai akhir.
Okay, contoh kan doktor, seorang tu dia take part by yang doktor kata GUI tu kan, and the others member dia ambil bahagian explanation and so on tu. How about the others member?
Kalau seorang buat demo saja, yang lain tu macam mana?
You kena collaborate lah. You kena bersama-sama.
Maksudnya buat satu meeting untuk discuss overall punya GUI lah.
Yeah. So
just only demo for video tu untuk GUI saja, bukan untuk daripada kita explain introduction and so on what we do for the project. After that baru ke tu.
Actually the overall sebenarnya you menceritakan keseluruhan macam mana you design, you kena tunjuk lah, you kena explain lah. So that means since the process is long, so you boleh cepatkan video tu sebab dia ada banyak proses buat daripada awal macam mana you buat you design the coding and so on, and then you get the results. So you need to show the step by step. So that means the way
Kiranya
is
doktor,
boleh buat video yang laju lah, maksudnya you boleh buat
video tu kena tunjuk prosedur bagaimana kita buat GUI.
Just only the procedure lah. Okay.
Yeah, the
GUI
from
prosedur
the
sampai
until the end. Yes.
No need introduction and so on lah kan, betul doktor? Conclusion or what tu tak payah lah kan?
Okay. Just you boleh cakap sajalah introduction. So we are doing about what, and how we do it is that first we do like this, second we do like this, third process, fourth process, and then we put the input like this, we're gonna get the output like this. Like this, we're gonna get like this. So it means that a lot of process happen from the beginning until you get the results. So in that case, you boleh cepatkan video itu the procedure.
Minimum untuk video tu berapa doktor? Sorry, dia punya duration. Maximum, sorry.
There's no maximum. I'm not expecting 1 hour. Maybe 20 minutes, for example.
Okay.
So no need to be long. No need to be a long video. Tidak perlu long video. Cukup sekadar you tunjukkan proses melaksanakan projek ini daripada awal sampai you dapat results. Boleh ada tunjuk method macam mana resultnya macam mana. Boleh so you need to collaborate with all your friends. So kalau ada kawan yang tak bekerjasama, you boleh bagi tahu saya lah, kita akan tolak.
Dan doktor, saya nak tanya.
Okay.
Pasal fully complete punya video tu itu hantar minggu ke berapa
Study week is
so maksudnya untuk setakat ni untuk video untuk demonstration about the GUI, just the GUI part, then for the fully video tu hantar dalam minggu ke study week lah.
No, only one video. You are expecting 2 video actually 1 video. Maksudnya saya perlu satu video demo pada akhir semester, pada akhir minggu. Saya Q&A. Nanti saya akan buat satu Q&A session yang mana saya akan tanya soalan. So before the Q&A, maybe you can upload your video first.
Jadi yang full complete punya video kita just attach dengan intro dengan conclusion sajalah. Betul tak?
Intro dengan
conclusion.
Because I want to see your process, your GUI process.
No need the slide for introduction, right? Dengan conclusion kan doktor. Tadi doktor cakap just cakap on masa kita nak tunjuk the process saja.
Saya tidak perlu tengok slide. Saya nak tengok macam mana you buat MATLAB tu. Okay. Boleh. Adakah explanation saya menjawab soalan? Sorry.
Sebab biasa report dia nak buat intro, conclusion dengan result semua sekali. Itu dinamakan video video presentation project.
I'm not expecting you slide. Tidak perlu tunjuk slide. Saya cuma nak tengok video MATLAB.
Video MATLAB.
So you need to explain to me how you do the MATLAB from the beginning until you get the results. You kena tunjuklah kalau masa you buat proses coding coding GUI, and then after you finish, and then you put the values, and then we get the graphs. You put another value, we get the graph. It's a demo,
Okay.
demo of the MATLAB, demo of your GUI. So whether you want to put your slides, it's up to you. Slide is actually helping you to explain. That's all. But
Okay.
I want to see the GUI. That's it.
Baik,
Boleh?
Doktor.
Doktor, I have
Okay,
one
silakan.
problem, which is my friend WhatsApp me because he cannot attend into the class back.
Okay. Okay,
Then dia
siapa
tak,
lagi belum?
maksudnya dia kena ni apa tu? Dia kena apa dia tak boleh masuk. Kalau masuk
Siapa
je
nama dia?
ask
Nama
me
dia
to
siapa?
join. Nur Salwa,
Nur
nombor berapa
Salwa. Okay, 36 ni.
Alright.
Doktor, nama,
Okay.
nama saya dah.
Thank you doktor.
Siapa lagi tadi?
Muhammad Syahrul Hamizan.
Okay, Syarul.
Okay, thank you, Doktor.
Okay, welcome. Siapa lagi?
Bye. Assalamualaikum.
Salam. Ada lagi? Tadi pelajar yang bertanya soalan pasal video dah clear.
So far dah clear doktor.
Okay, so if you ask me, I just want to see the process of your MATLAB.
Oh,
Whether
okay.
you want to put inside the slides is up to you. The slides is actually want to help you for the explanation. That's it.
Oh.
Okay.
So overall Doktor cuma nak tengok apa yang kita prosedur yang kita telah buat dalam MATLAB GUI saja kan?
Ya. Saya nak tengok macam mana you buat programming. You kena tunjuk saya step 1, step 2 macam mana. Dia ada banyak steps kan. Bila kita program, we want to program about this GUI part, so we do this programming, and then we do this programming, and then after complete, we do the testing. We put inside the input. What is the output?
Right.
You show the demo to me. But before you demo the final product, I want to see how you do the product. So you need to show how you do the product, and then you demo the product in the video.
Okay.
Okay.
Baik.
Sebab dia punya proses panjang kan. So
proses dia panjang.
itu sebab saya katakan salah satu teknik yang you boleh buat, you boleh lajukan video itu So ada part yang you lajukan video. So you boleh nampak lah ada step until you buat demo akhir. So nanti masa Q&A saya cuma tanya soalan saja.
Okay.
Okay.
Thank you.
Boleh
Boleh.
Later you can ask me in the group, no problem. Nanti bila saya ada rubrik nanti maybe lebih clear. Sorry saya rubrik lambat sikit, sorry.
Sebab tak ada rubrik, kita tak ada
I will give you as
kita
soon
tak
as
ada
possible.
attention nak buat benda tu.
Okay, I will give the rubric as soon as possible. Sorry about that.
Okay.
So that's all for now. Okay, thank you. Bye-bye.
Thank you, Doktor.
Okay.
Terima kasih.